Right, so we'll start with this lecture. Let's do a quick recap as to what we had done in yesterday's lecture. So we talked about, the day before, we talked about a common form of the equations that we'll be dealing with in this course. Okay, it's good to have a common form so that different kinds of equations can be obtained by putting the value of parameters differently. So what happens is that mathematically you have to deal with only one common form. You don't have to I don't have to keep talking about heat conduction, fluid mechanics and so on. We'll only talk about the terms of the equation mathematically. So first we have to appreciate the fact that there exists a common form and all the equations that are of interest in fluid mechanics can be boiled down to this common form. So we deal with equations such as mass, momentum, energy and species balance, and in these equations the common form for some unknown phi. Now phi I have written as a scalar, but phi can be vector as well. Okay. So phi is the unknown dependent variable that we are solving for in the equation as a function of spatial coordinates x, y, z and t in the most general case. So we have four terms in this common form. The first one is called the transient term, which has the derivative, partial derivative with respect to time. The second one on the left hand side is called convective term. This is the term that is responsible for convecting the information because of flow. So if you have a flow happening, it will, if let's say you have a species, some salt in the water, and then you put some salt and the water is flowing. So what you will see is that the salt front will start moving from left to right if the flow is happening that way. So flow carries information with it, so that's called convection. You may have seen that if you put a dye or a color in water, it will get transported with the flow. The third term in this equation, that's the first one on the right hand side, is called the diffusion term. So diffusion we all understand. So if there is no air flowing in the room, let's say I switch off the fans and I spray perfume in the center of the room, it will diffuse with time because of molecular diffusion. Now the physical reason for diffusion could also be something else. In that case we call it dispersion, but mathematically we model it as the gradient of the unknown phi. That's called the gradient diffusion model. You may have learned about it in your other courses where you have written the equations for fluid mechanics or heat transfer. And the last term on the right hand side is called the source term, which is responsible for creating something. So let's say if you're talking about energy equation where you have heat, so it could be some electrical element in some place in the room that is generating some heat, so that's a source term, because that's neither convection nor conduction. So everything, in fact anything that is not a part of these three is usually put in the source term, mathematically speaking. You can do that. So phi is a quantity per unit mass, that's how we have written the equation. So when you multiply density with it, you get quantity per unit volume. So we tend to write equations in the units of per unit volume so that things can vary with space. So phi, all the parameters here are typically written as functions of the x vector, which is the position vector. So that is the function of x, y, z coordinates in the domain. Now the diffusion parameter gamma and the source term s can have physical meaning depending on the situation that we are dealing with. So if you are dealing with phi being let's say mass, in this case our s becomes 0. But if you are dealing with phi being momentum or phi being a velocity component, because it's quantity per unit mass. So momentum per unit mass is velocity. That's the intrinsic variable. So we deal with phi equal to, let's say, one component of velocity, that's the x component, that is u. So in that case your source term becomes having the body force plus the pressure force. Okay, is that clear? So please don't get confused as to how to find these values. I mean, you know the equation, you know the final equation. All you have to do is I give you a template, a common form, and I give you the actual equation. All you have to do is find out what term is what, that's it. So if you see that the s in this case corresponds to two terms here, so that s is equal to this term. You don't have to find the equation here, the equation is already available, we are just trying to fit it to the common form. So that's where we stopped and we'll continue from here today. So by the way, you should be able to see the lectures on Moodle. So we are sharing PDFs on Moodle. Yes, yes, please. If you are late, then don't ask. Okay, feel free to come in. I would want to talk a bit about vector calculus, just to do a quick recap, because sometimes it just forget about it. So in this case, so it's a recall. Don't expect to learn it from scratch. We're just recalling it. We'll only deal with Cartesian coordinates here. And that is for simplicity, because I don't want to stress you with other coordinate systems which are slightly more complicated to work with, but the ideas that we are discussing are valid for any kinds of coordinates, as you have seen that we are using the coordinate free equations. So the first operator, or the most important operator in vector calculus, is the nabla operator. Which is defined as in a 3-dimensional, so we'll call it in 3D. Right, so that's the nabla operator, and please remember it's an operator. It needs something to be put into the brackets so that it has meaning to it. It's a vector operator. Unlike our understanding pre-vector calculus times, operators can also be vectors. So if you put a quantity here, it will give you a vector quantity back. Typically we put scalars into this operator, but you can also put vectors. But for that, if we require that, we'll discuss it. Otherwise, we'll assume that you only put a scalar into it. So if I put a scalar phi into this operator, or supply it to this operator, so what I get is partial derivative of phi with respect to x I hat plus partial derivative of phi with respect to y j hat plus partial derivative of phi with respect to z times k hat. So that's the meaning of grad of phi. We tend to call it grad of phi. Now there is another, well, since nabla is a vector operator, like you can take dot product of two vectors. So you can take a dot of nabla with some vector quantity u, let's say it could be velocity. So then the first thing you do is, before you put the values into operator, you do the vector operations. So your u has components which are, so let's write it this way. So you write a vector typically as components x, y, z with commas. So we'll use that form. So that's the first vector. The second vector is u v w. So when you take a dot product of u and v, you get u1 v1 plus u2 v2 plus u3 v3. So we do that. So the first one is del by del x of u, because now when you do the first x component times the second x component, then you have to supply the u into it, plus okay. So this is what we get if we take the divergence of a vector u. Now with these ideas I can take the divergence of the gradient of phi, that just implies from the ideas above. So gradient of phi was this, and divergence is I have defined using this idea. So all I will get is del by del x of the x component of this, which is del phi by del x right. So this simply becomes del 2 phi by del x2 plus del 2 phi by del y2 plus del 2 phi by del z, and this is also called the Laplacian of phi. So if you have a square over del, it actually means this thing. So I can actually write it's 3 lines. So this is definition of Laplacian of phi. Sorry. It's a divergence of the gradient of phi. Is that clear? Now you may have seen, if you have been through the second chapter in the book by Patankar that I was given as reading assignment, you may have seen that they are using indicial notation. Okay, so that's another notation that is typically used, where you have indices rather than you have these symbolic notation. So that can also be used, but that is something we will not discuss in this course. If you have not been through any experience with indicial notation, it takes a couple of lectures to pick it. So I will suggest it's very important to understand it, because you should be able to read all kinds of books, and it's actually quite a rich notation. I personally prefer that notation over this one, but this one is firstly, the symbolic notation is the first one we are introduced with typically, and the other one is that this is written in a coordinate free form. If you have a Laplacian of phi, then the Laplacian of phi can be either in Cartesian coordinates or cylindrical coordinates or spherical coordinates or some other coordinate system. Okay. So I will just make a note here that indicial notation will not be discussed in this course. It's good to learn it. So if you get an opportunity to learn this notation, please jump over it. Right. So we move on. Not now. So when we need it, we will discuss it, okay, because that will just confuse us at this stage, and I don't want to do that. I want to discuss some more foundational ideas first. If you want to know it, you can discuss with me later, okay. Right, so let's before we actually jump into classifying the equations, let's talk about an important idea which is called well posed problem, or a problem being well posed. So what is the meaning of well posed? Anybody knows about it or wants to comment? So let me give you an example. So let's say we have a one dimensional situation. So let's say you're talking about the temperature of something along a bar. So you have a one dimensional situation where the bar has a length L, and for some using some ideas, we have developed this equation where the second derivative of temperature theta with respect to x is 0. Now we want to solve this. Now physically speaking, if an experiment was happening, if you have a reality, you will have a unique temperature at a given point, right? You cannot have multiple, like in mathematical equations can have multiple values. You cannot have multiple values in reality. In reality, you have a unique solution. So we have to make sure that our mathematical model should also mimic this quality of having a unique solution. Now let's solve this. So if we solve this, we get theta is C1x plus C2, C1 and C2 being constants. But C1 and C2 can be anything. So that means the solution is not unique. I put different values of C, I get different solutions for theta. So how can I ensure that my solution is unique? Anyone? Raise your hands and then speak up, please. You wanted to speak up? Raise your hand. Raise your hand and then yes. Boundary conditions, right? So we have to supply some conditions called boundary conditions. That is, we want to supply the values of theta at the two boundaries x equal to 0 and x equal to L, so that we can find the values of C1 and C2. So I can have a boundary condition. First one, that let's say the temperature at x equal to 0 is theta naught. some constant, some value. And then second boundary condition, that temperature at the length L is theta L. With these two, I can substitute that into my solution, because the solution is valid, the equation that we are solving is valid in interior and boundary. Just please remember that. Sometimes we get confused that the equation is valid in the interior of the domain and boundary we have boundary conditions. No, it's valid everywhere. It's the physical reality of, it's a mathematical modeling of the physical reality, and that's happening everywhere, including the boundaries. So in that case, this solution that we have got, that is also valid at the two boundaries. So if you substitute that, you get C1 and C2. Now the boundary conditions could be different. You could have supplied, instead of supplying the values of theta at the two boundaries, I could have supplied d theta by dx at x equal to L. Let's say that is theta some tilde L. You can substitute that and you can also get the values, right? And you have done that in courses such as fluid mechanics and heat transfer. You have done this exercise whenever you try to solve equations analytically for special cases. Is that clear? Any questions? So second order equation, we had two constants of integration, so we needed two boundary conditions. Now if we deal with a two-dimensional situation, so now we are solving partial square of theta with respect to x, well this one, except that you only have x and y, there is no z. So you will do sort of two integrations, so you will get four constants, two in x direction, two in y direction. Again, those who have learnt about the method of separation of variables, you may have seen that when we solve this equation analytically for special cases, we integrate them and we get four constants, right? So we have to obtain four constants. So we need four boundary conditions in this case. So they could either be supplied at the four boundaries, or I could have supplied it at two boundaries and then I could also supply the gradient at those boundaries. You don't need boundary conditions everywhere on all boundaries. I can have boundary condition on the left boundary, both the value of theta supplied and the derivative of theta supplied. You can check for one dimensional situation, that will work. Okay. So we need four boundary conditions. So as you increase the number of dimensions, the boundary number of conditions required increases. So how do we ensure a unique solution? We need a governing differential equation. We need boundary conditions. And sometimes what happens is you are also dealing with a variable called time, like we had the transient term in the first part. So you will need, mathematically speaking, you will need boundary condition for that variable also. But you cannot have a right boundary condition for time, right? Because it doesn't make sense. You are solving for a value at a given time, it cannot depend on time value at a later time. Time, what is happening now only depends on what happened in the past. And that is the reason you only have, well, that is not the reason, but that agrees with the fact that our, let's write the general form again. So this was the transient term, and you can see that this is first order in time, unlike x and y where it could be second order, we have Laplacian, but here it's only first order in time. So that means you only have one constant coming from it, so you can use only one boundary condition for time, which is called actually initial condition. Just to clarify, just to differentiate between time and spatial variables, but actually that this is nothing but a boundary condition in time, but we call it initial condition. Okay. So if we need this, we will populate it again. Any questions? So let's talk a bit more about boundary conditions. So right now you might feel that I am going a bit fast, but this is because these ideas are quite relaxed. So when we start talking about new advanced ideas, I'll actually go slow. I'll give you time to absorb things as well. So boundary conditions, we'll talk about classification. What are the different types of boundary conditions, but this classification is mathematical classification. So depending on the physical situation, that classification may have a slightly different meaning as to what that means. So the first type is called Dirichlet boundary condition. So that is when you specify the value of theta or the unknown variable, and that is called Dirichlet. So like we do, the temperature at the left boundary of the bar is 0 degrees because that is dipped in melting ice. So that's Dirichlet boundary condition. The other type is called Neumann boundary condition. So in Neumann boundary condition, you specify the derivative, the first derivative of theta at some boundary. So this is at a boundary. So this condition becomes Neumann boundary condition. Now in one dimension it's simply d theta by dx, but in two dimension it's actually slightly different because then we have to specify things in terms of gradient. So you know directional derivative, right? So in that case we have to specify directional derivative. So grad theta is simply the gradient of theta, and when you take a dot with a certain vector, unit vector, that gives you the change in theta in that direction. So this is also called d theta by dn. Okay, so you specify that. So this is at the boundary. And the third one is called Robin boundary condition, that we do not encounter too often, but we do that in heat transfer. So in that, this is simply a linear combination of 1 and 2 of Dirichlet and Neumann. So what that means is that we will specify theta times C1 plus C2 times d theta by dx equal to some theta tilde naught, and this complete is at a boundary. So heat fin problem, again if you want to recall, it doesn't really matter if you can or cannot recall, but that is where we get this. In convection situations we get this Robin boundary condition. So when we will actually in this course discuss it at one stage, so there I will highlight it again. It's simply a linear combination. So theta and d theta by dx are not specified separately, but some linear combination of that is specified. So you have to learn how to. So our job will be to learn how to implement these boundary conditions mathematically. Is something happening outside that's distracting you? You can switch. You can close the door if that is the case. Okay. I think AC has been switched on, so now you can close the door. विशाल 2 मिनट बाद ना सारे विंडोज ही बंद करते हैं. So let's have a couple of questions just to understand things better. So we have this equation Laplacian of theta equal to 0 that's being solved in a two-dimensional situation. I supply a Dirichlet boundary condition here, theta top and theta equal to theta, let's say bottom on the bottom boundary. Is this problem well posed? How many people say no to the answer? Only a few. How many people say yes, it is well posed? No hands is worrisome. So this is not well posed, because if you look at the equation, so we'll integrate it in different directions. So this gives us two constants of integration, and this gives us two constants. With these two conditions, we can only find two of these four constants. So that means you do not have a unique solution to the problem yet. So we need two more conditions. So this is not well posed. We also call it ill posed problem. And see, it's very important to have a problem which is well posed. Otherwise, you'll start trying to find a solution, but you will get a different. You might get a different solution every time you solve it using numerical techniques. And that the reason was not because your method was a problem. The problem, the issue was that we did not start with a well posed problem. So we do have to give it a thought whether the problem that we are starting with mathematically, is it well posed or not. So we should always take a break and try to figure out whether that is the case or not. So what about this? Same equation in one dimension now. d2 theta by dx2 equal to 0. We just solved it. It has two constants of integration, c1 and c2, but both the boundary conditions are Neumann. Is it well posed or ill posed? How many people say it is well posed? Proper raise of hand. If you are confident, you raise your hand. If not, then you don't raise your hand. How many people say it is ill posed? Just one correct answer. It's ill posed. Let's see. So the solution was, if I give you the derivative, what I am giving you is d theta by dx, which is c1. So if I give you d theta by dx, all you can find is c1. Once you take a derivative of theta, c2 is lost. So if both conditions are Neumann, they actually are the same condition. They cannot be different. It's a linear, the solution is linear. Let's say it's dropping. So this is the left boundary, this is the right boundary. If it's a linear solution, the slope here and here are the same. I cannot supply two different Neumann boundary conditions. If I do that, then you don't get a solution at all. Then that means there is no solution satisfying those conditions. Okay, so this is an ill posed problem, because with two Neumann boundary conditions, you can either not have a unique solution, or you may not have any solution at all if you specify the boundary conditions which contradict each other. Is that clear? You cannot have different values of slope here and here. There can be only one slope. So only one Neumann boundary condition can be useful in this case. To find this constant, you have to get a Dirichlet or a Robin boundary condition. Now these ideas are typically not discussed in books. So this is you'll only find this discussion typically in classrooms. Well, one of the most important ones and one of the most confusing ones as well. can the order of the boundary condition be the same as the order of the governing differential equation? So, what I mean to say is, if I am solving the Laplacian of theta equal to 0 in this situation, can one of the boundaries be how many people say no? Raise your hands, please. Okay, the one at the back, yeah, orange shirt, yes sir. You, yeah, that's orange to me. Why? Exactly, very good. Please sit down. It's contradicting the governing differential equation. I told you governing differential equation is applicable on inside the domain as well as the boundaries. So if that is the case, then I have already told you Laplacian of theta is 0. Then you cannot have Laplacian of theta equal to something which is non-zero on the boundaries. Okay? Is that clear? So let's summarize the aim of this course. So we need a framework being a tool or some box, black box, well not a black box, we want to know what's happening inside it. So we need a framework which solves a given differential equation or a given form of a differential equation, and it applies a certain method to solve it. It could be finite difference method, finite volume method. We'll discuss about these methods later, but there are different methods available. That's enough to understand at this stage. So we need this kind of a framework which can solve a given differential equation. It's very difficult to develop a framework that works for different kinds of equations. So we have given you a common form. We'll look to develop a framework which can solve that kind of a form of an equation. Now, of course, you will have to supply some inputs into this framework that you have. So you supply, if you remember, in the first lecture we said that if you want to solve something in a given domain, you have to put mesh points or node points where you will find the solution of the unknown phi. The more number of points we put, the better accuracy we get at the cost of more computational overhead. Okay, so this is called a meshed domain. In a domain you put some points and that becomes a meshed domain, loosely speaking, but that is what you have to supply to the framework. The other is you have to supply some physical parameters. Okay, although you have a common form, but you do not know what's the value of the diffusion coefficient. So that depends on the physical problem that you're dealing with. It could be viscosity, it could be thermal diffusivity or something like that. Then the value of gravity, for example, if you're dealing with some gravitational force as well, or in that matter the S, the source term, could have other terms as well. So we have to specify, we have to feed that into our framework. We need boundary conditions that again have to be fed to the framework. Initial condition, some numerical parameters. So numerical parameters, again we'll discuss it over the course of time. So it could be something like a tolerance. So let's say you are converging some iterative solution. Now ideally you will never have a zero error. The error will just go down as you have more and more iterations. You have learned numerical methods at some stage in mathematics. You know that if you are adding infinite number of terms and the series is converging, the more number of terms you add, the closer you get to the exact solution. But you will never get there exactly. For that you need infinite number of terms, which is theoretically impossible. You only tend towards it. So how close are you to the actual solution? That is your choice. So we can supply a tolerance, and that if the error is less than 10 to the minus 7, for example, then we are happy, let's stop. Otherwise your computer will keep going on. And there are some other constraints as well regarding machine precision, how small a number can your computer hold and so on. So these numerical parameters have to be fed to the framework as well. And sometimes we deal with the non-linear problems, so for that we need some non-linear parameters and so on. Okay. So at this stage all we need to know is, in addition to physical parameters, we also need some numerical parameters, because we are solving the equation numerically. So once you do that, what do you get out of it? You get phi as a function of x and t, but this x and t is not every x, it is only the mesh points. So I will call it x naughts. So this is only mesh points, not every arbitrary point. You can do interpolation. If you know the solution at 2 points, you can find solution between them using some interpolation ideas. But sometimes readily phi is not usable. If I know the temperature, I cannot do something with it quickly, but I can calculate some average quantities from it. Like heat flux, how much of heat flux is entering a given boundary, or I can find shear stress in if you are dealing with, just having a velocity will not be useful. You can find the shear stress, and that can help you calculate drag force. So we can calculate average quantity. That's post processing. So this is called post processing. This that you supply is called pre processing. And this, you may have guessed, is called the actual processing. This is where the calculations happen in the computer, the major amount of calculations. Is that clear? Questions? Is somebody waiting outside? Right. So as promised, I will show you a quick demo of, so only take 2 to 3 minutes, of typically what you do in a situation where you are writing a program. So this is typically what you will be able to do towards the end of the course. So this is your final assignment problem or course project, something similar. So the problem we have here is that you have a pipe which suddenly expands. It has a name called backward facing step, but it is simply an suddenly expanding pipe. There is no gravity here, but what happens is that when there is a flow happening and then suddenly an expansion happens, what you see is that there is a region where the flow starts to circulate. So the fresh flow will only go from here to here. This region will simply keep circulating. Okay. I mean, why are we solving this? Because sudden expansion can have a significant effect on the flow situations in pipes, but for now let's take it as a numerical challenge to solve it. So this is a code written in Python that you will be able to write towards the end of the course, and you can see that it's not a very complex code. It's just that it has a lot of stuff into it, but over the course of this period you will be able to do it yourself. So once we let's run it. So you can see that it has started to do some calculation, and now rather than waiting for the calculation to finish, I will show you a video which is simply an animation of this result. Okay, so it's on a loop. You can see that as time proceeds, we start to see this circulation develop. In fact, on the top also we get some circulation, which was not expected. Okay, so you can see CFD can actually give us insight into this flow situation, and in this case we are also plotting the u velocity, so we can find out where the separation, at which point the separation happens. And flow separation can have a lot of effect on the mixing inside the flow and so on. So you will be able to do this by the end of this course, right? And you will be able to write this code yourself. So we will stop here now. Any questions? Okay. So thank you very much, and I will see you next week.